Hi folks, if you're watching this today, these are the 3.7 notes from Chemistry 12, and this wasn't covered in class, but I'm going to go through it quickly. And what it is it's looking at what's called the common ion effect for saturated solutions. So where we have a salt and ions present in equilibrium, and how we can shift that equilibrium using Le Chatelier's principle by adding a common ion or in fact removing an ion from the solution by precipitation. So it's actually pretty straightforward. We already know Le Chatelier's principle tells us that when a stress is applied to a system at equilibrium, the equilibrium will shift in order to counteract that stress. The same thing is true. This is just another type of equilibrium when we have a saturated solution. It's just like any old equilibrium. What is true about it is that I can change my ion concentrations. If I were to change the concentration of my aqueous ions, that would, if I increase them, it would shift this equilibrium to the left to produce more of the solid, more of the precipitate. And so that's exactly what we do. So we could force this equilibrium to shift to the left by decreasing the solubility, or in other words, adding some ions here. When I make more precipitate or more solid, that means I have fewer ions after the shift, so after the shift to the left. So when we have more solid, or we have a shift to the left, we say that that's a decrease in solubility. Just remember what solubility means. Solubility refers to how much solid has dissolved. So if we're shifting left to make more of a solid, we're decreasing the solubility. So let's look at how we do this. So we have an example here, calcium carbonate. In equilibrium, a saturated solution of calcium carbonate gives us calcium 2+ ions and carbonate ions in solution. If we were to increase the calcium concentration, so if I were to add some calcium 2+, for example, how would I add that? Let's think about that for a minute. Down below, if I were going to add some calcium, there's no bottle that I'm going to find sitting on a shelf that says calcium 2+. So I would add some calcium nitrate. Remember, we pair up all our cations with nitrate to make that cation soluble. So if I added some calcium nitrate, which would then give me nitrate ions and calcium ions, that would cause a shift to the left. The equilibrium would try to counteract that change by using up the calcium 2+ ions, which will produce more solid and thereby decrease the solubility of my precipitate. The other thing I could do is I could add some carbonate ions. So again, I could add or increase the concentration of carbonate. How would I do that? I would have to add, so what I would actually add here would not just be carbonate, but I'd pair it with sodium or any other alkali metal or ammonium, just so that I have a soluble solution of carbonate. So in this case, I would add some sodium carbonate, which gives me more carbonate ions, and again, that shifts it to the left. So these are called common ions. So adding more of one of the ions that's already present in equilibrium shifts us to the left and therefore decreases solubility. And that's the summary of the common ion effect. A compound of low solubility, in other words, one that can form a saturated solution, the addition of either of the ions present in the saturated solution from a compound with an ion in common will decrease the solubility of the compound with low solubility. In other words, it will shift it to the left and make more of that solid. I'm not going to go through this chart. I think that it's just giving some examples, but maybe I'll just pick one. So not any old ion is going to shift my equilibrium to the left. It has to be an ion, or a compound that I'm adding has to contain an ion that's common. It's either got to be calcium or carbonate ion that's present. So I'll just pick one here, for example, like potassium nitrate. If I added some potassium nitrate to this equilibrium above, the ions that I would be adding are calcium ion and nitrate ion. What would the effect on solubility here be? Well, none, because I'm not adding any extra of either common ion. So there would be no shift. So there would be no effect. I do want to also look and say, hey, when I add a different compound, is there any chance of it precipitating one of my ions? And that's what we're going to look at next. In this example that I just used with potassium nitrate, both potassium and nitrate are soluble with all ions. So potassium is an alkali metal, it's soluble with all the anions, and nitrate soluble with all the cations. So there's no precipitates being formed either. Okay, so there's also no precipitates, which tells me that I'm not going to be taking any of those ions, calcium or carbonate ions, out of solution either. So how do we increase solubility then? How do we cause more of that calcium carbonate to dissolve? Well, there's a few different ways. One is we could heat it up. Usually when we increase the temperature, that will drive this equilibrium to the right as well. Solids dissolve at a faster rate in warmer temperatures. But we could also change the concentration of ions using Le Chatelier's principle, and that would drive my reaction to the right as well. That would cause a shift. So to increase the solubility of a salt, we can stress the equilibrium so it shifts to the right by removing or decreasing the concentration of either or both of those ions. It's pretty hard to sit there and pick ions out of solution. We can't see them, so we can't physically extract them from our solution using a mechanical process, but we could add another ion that would form a precipitate with one of those two ions that I have. So we're going to add a substance that precipitates or removes one of my common ions. There's also a special exception here where if we have carbonate present, as we do in this example, only if carbonate is present, we can actually add an acid. And we'll look at that in just a moment. That's just an extra way that I can do it, because if I add an acid, the H plus from the acid will actually form a compound with the carbonate ion, which then again removes it from my equilibrium. So let's do an example of this. Okay, I've got a different saturated solution here. This time I have silver chloride with silver plus and chloride negative ions in solution. And we could decrease the concentration of silver ion or chloride ion by precipitating one of them out of solution. If we did that, the equilibrium would shift to the right. Le Chatelier tells me if I lower the concentration of an ion, that will shift my equilibrium to the right. It will try to make more of that product. How could we do that? Well, let's consider one of our ions. Let's start maybe with silver plus. So let's think about it. What could I add? I use my solubility table, or my solubility of common compounds, the table I have in my data booklet, and I look for some ion that's going to form a precipitate with silver. And I see that a good choice might be some S2 minus, some sulfide ion. That would form a precipitate. It gives me silver sulfide when I add it to silver. And so if I added some sulfide ion, that would precipitate my silver out of solution. How would I add it? Of course, I can't just find a bottle of sulfide ion on a shelf. So I'll pair the sulfide anion with sodium. So I'll add some Na2S, which is really just Na plus and S2 minus. right? So I would go ahead and add that, and it's going to form a precipitate, which means I've decreased concentration of Ag plus in my equilibrium. And Le Chatelier will tell me that that causes a shift to the right in order to make more Ag plus. So now more of my AgCl solid is going to dissolve. So the equilibrium shifts to the right towards the products to make more. And the solubility then increases. Okay, because more solid dissolves to replenish that silver plus ion. I could have also forced a shift to the right by precipitating out the chloride from my saturated solution. So again, I look at my solubility table and I ask myself, what's a good positive cation that I could add that would make a precipitate with chlorine? And you look up chlorine and see what has low solubility with it. And there's a few choices, but for example, lead 2+ would be a good choice. And so what I would actually add is some lead nitrate, because we know nitrate is soluble with all cations. So that would allow me to introduce my lead into solution. And I would get a precipitate forming, which would be lead chloride. So I have decreased the concentration of chloride ion. That causes a shift to the right because my equilibrium wants to replenish some of the chloride that I've removed. And again, I've increased the solubility of my AgCl. So the solubility of my AgCl solid has increased because more of that solid has to dissolve to replenish those ions. Finally, we have one other way of shifting in equilibrium to the right, or in other words, another way of removing an ion from solution, but it's a special circumstance when we have carbonate present. So if carbonate is one of my ions, I can add an acid to my equilibrium, so to my saturated solution. So for example, if I added some hydrochloric acid will break apart in water to give me H plus and Cl minus. The H plus here is important because the H plus is going to react with my carbonate ion. So we'll have a look down here below. So here's my carbonate ion in solution. It reacts with that H plus. So H plus ions will come in and attack it. And it will allow attack from two hydrogen ions because it has a 2- charge. So it will be attacked once and then again, which gives us something called H2CO3, otherwise known as carbonic acid. And carbonic acid is quite unstable. If carbonic acid forms, it immediately decomposes. So we get this compound. So it's very similar to a precipitate, except it's not a solid. It's just a compound in my solution. And then it breaks apart. So here's the decomposition of carbonic acid. It breaks apart to give us water and carbon dioxide. The carbon dioxide escapes if this is an open container. And even if it doesn't escape, even if it's a closed container, it's still going to bubble up, and that gas is going to be sort of in my beaker. But the carbonate ion is now gone from my saturated solution, and I'm left with some additional water here. So what happens is, again, this is just a different way to remove some carbonate. The equilibrium will shift right in order to produce more carbonate ion because we've disturbed the equilibrium, and that also increases the solubility of my solid salt. So for the most part, we look at using a precipitate, but when we have the special circumstance where carbonate ion is present, we can also add an acid to increase the solubility of our compound. And this is just summing it up here, so I don't think I need to go over this. It says the carbonate decreases, the reaction must shift right. But I think I just said all that. And the solubility increases because we dissolve more solid. So that's the basis of the common ion effect. It's not really anything particularly different than our Unit 2 notes about shifting equilibrium and Le Chatelier's principle, but it is interesting because it's really applicable when we have a saturated solution. It's possible to predict what's going to happen if I add another compound, and it's also possible to increase or decrease the solubility if I wanted to by stressing that saturated solution in appropriate ways. Thanks for joining me. Bye for now.